Hi everyone, this is Chiranjeevi, and in today's video we are going to solve the coin change problem. So let's look at the problem statement first. So this is the problem statement for coin change problem, which says given an infinite supply of coins of different denominations, find the number of ways to make change for a value n. So let's try to understand what this problem statement is asking for. So what it says is you have infinite supply of coins of different denominations. So it means you have a set of coins which has different denominations. Let's take 2, 3 and 5 for example, and you have infinite supply of each of these coins, which means you have infinite number of coins of denomination 2, of denomination 3 and so on and so forth. Along with that, it also says that you have to make change for value n. So this is also an input parameter to your problem, which says n. Now this n could be a positive integer. Let's say in our case it is 7. So now the problem statement would be like, using these coins of denominations 2, 3 and 5, how many ways you can make change for 7? So let's look at how many ways are there to make change for 7 manually first, and then we will try to think of a way to solve this problem using our intuition. So if you see, there are only 2 ways to make a change for 7 with these coin denominations. And those are 2, 2, 3 and 2, 5. Let's try to deep dive into this problem and see how we can solve this intuitively. We will be using recursion to solve this problem. Now in a recursive problem, you always have a set of decisions you can take at every step while solving the problem. So in this problem, you have these 2 options which you can choose from while solving that problem. So let's say you want to solve this problem for n equal to 7 using the coin 2, 3 and 5. Now at this state in the problem, you have 2 choices. The 2 choices are whether you can pick or select 2 to be included in the answer to make a coin change, or you completely discard 2 from your input set. So these are the 2 possibilities. So let me go through the recursion tree first, and then we will take a look at how to implement this using code. So this is our problem. We want to make change for n equal to 7 using the coin denominations 2, 3 and 5. So the first option which we have is we can pick a coin. So in the left side of the recursive tree, we are choosing option 1. So if we pick a coin, the problem changes to, can we make a change for 5 from the coins 2, 3 and 5? And how did I get this 5? What I did was I have already picked this coin 2. So now I only make a change and have to make change for the number 5, because 7 minus 2 is 5. Now on the other half, if I discard this coin 2, which means I don't want to use our coin 2 to make any change for 7, what can I do? I can completely ignore 2 and call the same problem for the other remaining coins, which are 3 and 5. Now moving down through the same path, in this recursive call also, we will have 2 options. We can either pick 2 again or discard 2 completely. If we do that, you see this number again reduces to 3, and we again have 2, 3 and 5 coin denominations. And on the other half, we are discarding 2 and we have the same problem with the reduced set of the coin denominations, which is 3 and 5. If we go one layer down again, you will see that we are again subtracting 2 from 3 because we are picking the coin as per in option 1, so which makes it 1. And then we are keeping the same set of coin denominations with the problem. On the other side, if we discard 2, we have 3 which remains same because we are not picking any coin, and we have a reduced set of coin denominations 3 and 5. Now if you see, interestingly, from here, no matter whether you pick a coin or you discard a coin, you are not gonna get any result, because even if you pick a coin 2, 3 or 5, any coin you can pick, it's gonna reduce the number to less than 0. And if your problem is reducing the number to less than 0, you can never make a change for that particular configuration. So I have discarded that entire subtree. Now if you come here, you can again pick a coin. So in this case, if you pick 3. Now if you have picked 3 again, you have left with the number 0. Now this number 0 means that you have successfully made change for the number 7 at this level, and now you don't have to make any change. So this yields a result of 1, which means if you go down this path, you will get 1 way to make a change for 7 using 2, 3 and 5. Now similarly, if you see, we can discard 3 also at here, and when we do that, we are not able to make any further changes because any picking or discarding will reduce the number and make it negative, and we will not be able to make any coin changes there. So this subtree is also discarded. Now remember that we only have one way right now figured out by which we can solve the problem. Let's go to the other half and see whether from this half is there a way to solve this problem or not. So let's go here, and if you see, we again pick 3, so we reduce 3 from 5, which makes it 2, and we also have to keep the same coin sets which we have, because that's option 1. You pick the coin and you keep the same set of coins with you. Now if you again further drill down this path, you will not be able to make any changes from point 3 and 5 because both 3 and 5 are greater than 2, and if you pick any of them, that will reduce the number to be a negative number, which is the case which we encountered here as well. Similarly, if we go down this path, now this path is going to have you have to make 5 from 5, so you can either pick 5 or discard 5. If you discard 5, you will be left with no coins, which will be 5 and with an empty set of coins. So here also you will never be able to make any changes, so no ways from here. And similarly, since we are able to reach 0 from this part of the tree, you will have one way from here also. Okay, so now if you see sub-recursive call, you are able to somewhere find one way to solve the problem, and what this recursive call will be returning is this way count. So in this part of the tree, so this will return a 0 count to this recursive call. This will also return a 0 count, but this will return a 1 count. Now you have went through all the 2 options. Now only thing you have to do is you have to add the value from option 1 and option 2. So this becomes 1, 0 plus 1 is 1, and this value is also returned from this recursive call. So this returns 1. Now again, in this part, you are returning 0. This part is returning 1. So how do you merge the results? You add it. So this is 0, this is 1. So this will be 1 plus 0, and this call will return to its parent with a value of 1. Now if we come to this line, here we know that we have the input no ways to find, so this returns 0. And here we know we have only one way to make the coin change. So we will go and make that, return that 1 from here, which will make 1 ways in total, which is 1. And now this 1 plus 1 will return 2. Let's go to the other half where we have to make change for 7 using 3 and 5. So if you see over here, there are no ways you can make any changes for 7 using 3 and 5 because any combination of this would not yield in 7, right? Because 5 plus 3 itself is 8, and even if you have multiple 3's, like 3 into 2 is 6 and 3 into 3 is 9, which, so anyway there is no way you can make 7 here. Even if you go down the recursive tree, you will find the same. So let's go once and see how it works. So if you pick 7, so the option 1 is pick the coin. So if we pick 3, 7 reduces to 4. If we again pick 3, 4 reduces to 1. Now you see both of these numbers are greater than 1, so you cannot reduce further from down this lane. So this call returns 0. So, and if you go to the other half, you discard 3 and you are only left with 5, and you cannot make a value 4 from 5. So this also returns 0. So this returns 0, this returns 0. So overall this call returns 0. Let's look at that part. You have to make 7 from 5 because you have an option 2. You are discarding 3, and there is no way you can make 7 out of 5 because even if you pick 5, at some point you are gonna get a number which will be less than the current coin you have. So this returns 0, and if you discard 5, you are gonna have no coins, so you cannot make 7 or change for 7 using no coins. So this also have a 0 answer. Now to merge these two, you will say 0 plus 0, so this returns 0, and 0 plus 0, this returns 0, and at the final top layer recursive call, you take the answer from the left, you take the answer from the right, and you add it. So 2 plus 0 is 2. So as we saw, when we were trying to solve this problem manually, we had two ways to make change for 7 using 2, 3, 5, and those two ways are 2 and 5 and 2, 2 and 3. So these are the two ways, and from the recursive call also you see that this is how we are going to solve that problem. So let's jump in and see how we can code this problem. Okay, so now what we are going to do is we are going to take that solution from the whiteboard and build a working code out of that solution. So let's get started. Now I'm going to explain the method signature I have created so far to solve this problem, and then we are going to put content inside this method based on the solution we have discussed to solve this problem. So this method takes array of denominations and an input value n as discussed, and apart from that I am using an internal utility. We should make this private, and we are using an internal utility method which will be helping us to make that decision where we were keeping a coin versus we were discarding a coin, and that decision will be made by this variable index. Now if you remember, we were reducing the scope of the problem on every sub-recursive call. We were just discarding that coin from the array list, but in reality we cannot just create a new array every time and pass it to the sub-recursive calls. I mean, although that is possible, but we should not do that. So to ease that process, we are making the use of this index variable. Whenever we do an index plus plus, which it says that okay, from this index up to the last index, consider that okay, these are your input array which are bound. Okay, so let's get started. We will first cover the corner scenario. So anywhere in the recursive call, if n becomes 0, this means that you have found one way to make change for that configuration. So we are going to return 1 from there. At any point, if n becomes negative, which is less than 0, which means that you cannot go further down the recursive chain. So these are kind of the base cases for the problem. So you have 0 ways to do that. Now the main part of the problem. Since we are let's write the main logic first, and then we are going to write this last base condition. So let's say that you can either select a coin. So when you're selecting a coin, we are going to pass the same denominations, and as I said that our index variable is keeping track of from this starting position up to the last. Those are the coin denominations you have to consider. So when we are picking a coin, we are not discarding any element, so we will keep the value of index same. Since we are picking the coin, if you have observed in the recursive call, we were subtracting the value from n, and we were subtracting the value of the coin denomination we picked. So we will say n minus the coin denomination. So denominations of, now this is the first part of the solution, and the second part of the solution is, let me write it. So we are still going to pass the denominations array because that contains our input set, but this time we are going to discard the value. So when we discard the value, we will say index plus plus. And what this means is, okay, don't consider this particular coin, consider everything after this coin to the last. And since we are not considering that coin, we don't have to subtract the value out of the input n. Now there is a small condition or glitch over here that you could possibly go out of bound for the array you have been iterating on, because in the recursive call you are doing index plus 1. All right, so what you have to do here, if you have n remaining and it is greater than 0, and also at the same time you have crossed the array boundary, which means index equals denominations dot length. So in this case, it means that you have crossed the array boundaries and you are not able to reduce the sum value to 0, because at every recursive call we are reducing the value of n, and whenever we get to 0, we say that okay, we are able to make a change for the given configuration. So if you have some values in your n remaining and you have discarded all the coins, that is also a bad configuration, and you have to handle that and you have to return 0 from there. So that is the code for this knife recursive way to solve the coin change problem. Thank you everyone for watching this video, and in the next video we are going to discuss the dynamic programming based solution to solve this coin change problem.